Hi, everybody. My name is Jeremiah Blanchard, and today we're going to talk about the fundamentals of artificial intelligence. So, to start off, I want to ask, what does it mean for something to be intelligent? What are the abilities we expect of intelligent entities? You might consider it the ability to engage in logical thought, to take two pieces of existing information, put them together, and derive something new. Or you might consider it problem solving, being given the structure and definition of a problem and having to assemble a solution. Many people think of decision making as a key hallmark of intelligence, being given an environment and a situation, being able to decide on a course of action. And of course, there's learning and adaptation, being faced with some situation, making a decision, and remembering the results of that decision later so that you can change your behavior. And you probably have other things you could add to this list too, because we could really keep going forever. There are so many things we might expect an intelligent entity to be able to do. So, to take a little bit of a different tack on this, we might consider trying to build a model for intelligence. And that's exactly what a man named Kenneth Craic did. He came up with what we refer to as the Craic Model of intelligence. Craic referred to what he called the intelligent automaton, or an autonomous entity capable of making decisions. And he said that in order to be considered intelligent, it had to have a few qualities. There had to be a few pieces to this model. And to start with, he said it must have a small-scale model of reality. It must have some version of its universe, some abstraction of the world around it that it uses in order to make decisions. But what that really means is that we need a copy of the reality that agent is living in. In the real world, that is practically impossible, because in order to have a full-scale model of the universe, you'd need a copy of the universe. And in a computer space, it's not really practical either, because you'd need an entire copy of the game space or simulation space to make this work. And that's not really practical. We have memory constraints, we have CPU constraints. So that's why we can't do a full-scale model. The other question is, why is a small-scale model good enough? Why can we act using a small-scale model of reality, even if we don't have all of the information? And to answer that question, we can really look to ourselves. At any moment in time, are you really thinking about how many windows there are in a room, how many lights are on, how many outlets there are on the walls, what's the color of the flooring? Probably at least some of these questions you answered no to, because we don't store all of the information. We don't have it all in our short-term memory at any given time. We only need a small subset of the information in order to engage in meaningful decisions. And by the same token, we can try to boil down the model of reality that our agent is using into only those relevant bits and pieces. Another piece of the puzzle is that the agent in this model must be capable of performing actions. It must be able to engage in a behavior that changes the world around it. So that may seem fairly straightforward, but then we have this question of what does it mean to perform an action, and where is the line that we draw between something that's autonomous and something that's driven by someone else? And the answer is that it's not clear. We don't know with any absolute where we should draw that line. And this is not a philosophy class, so we're not going to get into the details of where we draw that line, but it's important to recognize that this is a fuzzy area. He also said, this model also requires that the agent have knowledge of the effects of its actions. Now, that doesn't mean that it must be able to predict a sequence of actions all the way to the conclusion, and that if a butterfly flaps its wings in Florida, it will cause a typhoon in Japan. But what it does mean is that the agent should at least know how its actions will immediately affect the reality that it exists in. A good rule of thumb is that you could say that an agent has knowledge of the effects of its actions if it can make predictions in its model of reality. It makes changes to its model of reality based on the actions that it takes. And finally, the model requires that the agent use inference to make decisions. And all this means is that information comes in, and based on that information, at least in part, a decision is made. In other words, the decision cannot be completely random. It can be partly random. It can involve random elements. But there must be information that informs the process, that infers a result. And that's what inference means in this case. Now, that includes hardwired actions. There are plenty of actions that we as human beings engage in that are hardwired in advance. For example, if you've ever put your hand on a hot stove, you probably know what I'm talking about. If you did, when you did you just leave your hand on the stove? Did you consciously contemplate the action of burning your hand, realize it was hot, and pull away? In all likelihood, you pulled it away immediately as a reflexive reaction, because as human beings, we're hardwired to pull away from very hot things and very cold things and things that will damage us. And this is all hardwired into our brains. It's not something we make conscious decisions about. And by the same token, a lot of AI engages in this kind of hard-coded behavior. That does not mean it does not meet the definition of intelligence, because there are many levels of intelligence. We're not trying to limit this to human-level intelligence, but rather we need to cast a wide enough net that it will cover all intelligent actions of any kind, and that includes the actions of characters that may be driven entirely by instinct. So now that we have a model for intelligence, we might ask, what does it mean for something to be artificially intelligent, or why do we create artificial intelligence? And to answer this question, we have to look at the nature of humans and computers. Computers are really good at a few things. They're really good at crunching numbers. They're really good at arithmetic. They're really good at remembering things. If you store something in memory in a computer, it has immediate instant recall. On the other hand, some things that people are very good at, computers are notoriously bad at. Computers, by their nature, do not know how to solve problems, how to make decisions, or how to learn. Whereas human beings, this is exactly the type of behavior that we are hardwired for. We are hardwired to detect patterns. You can consider our brains giant pattern-matching devices. They find patterns, they match patterns, and they make decisions based on those patterns. So the idea here is that computers and humans are fundamentally different. We are really trying to squeeze a square peg into a round hole, and that is not easy. But our goal at the end of the day is to create at least the impression of intelligence. We want to create that special something, that spark that makes the AI feel real, that makes it feel like it's a real opponent or a real entity we're engaging with. So you may have heard me throw around this word agent, and in AI, we use this word a lot because it just means an entity of some kind that may or may not be self-driven. We refer to AI programs, to machines, to robots. We refer to all of these as agents. And there's a few different categories of agents that are useful for us to know about. Now, with that said, none of these categories are hard and fast buckets. You can have agents, and often have agents, that cross over the boundaries of these categories, but they are very useful for classifying behaviors, and that's why we use these definitions. The first one we're going to talk about is what we call the reflex agent. And this agent is entirely reactionary. Everything is hard-coded in some way or another, so that when an input comes in, there's an action that comes out. There is no deep thought process. There is no deep computation. It's an immediate reaction. And this kind of AI is actually very common in games and simulations because it is the simplest to implement and still often gives us very interesting results. A goal-based agent has a single goal, and it will single-mindedly pursue that goal, no matter the cost. A good example of a goal-based behavior is a path planner. We have to reach the goal, we are at a certain location, and we plan a path to reach that goal. The most complex category of agents is what we call a utility-based agent. And a utility-based agent is seeking to maximize its utility, which you might think of as happiness. And you can think of human beings in some ways as utility-based agents. For example, this morning you probably woke up and considered briefly going back to sleep, but in the end you decided to get up and go to school or go to work. And the reason for that is likely because you traded off the possible benefits of each of these scenarios. If you go back to sleep, you will be a little happier now, but if you go to school and you get your degree, or you go to your job and you earn money, you'll be a lot more happy later. And that is what a utility agent does. It trades off possible actions and selects the ones that will maximize its utility in the long term. It's also important for us to consider how an agent is going to gather up knowledge and make decisions about what it's going to do in the world. There are three main ways that we can acquire information in an agent, some more popular than others. We can cheat. We can gather information directly from the environment or engine, which players do not appreciate if they know is going on. We can also acquire information through sensors. Sometimes these are view cones, sound radiuses. You could even have smell radii if you wanted to. And communication, where different agents communicate with one another and pass information between themselves. Now, I said players don't appreciate cheating, and that's true if they know what's going on. With that said, sometimes it is the only option for us to really accomplish the goal, because some learning behaviors and some of the more interesting behaviors we can engage in can be very expensive. At the end of the day, our goal is to maximize the user's engagement with the environment. And whatever means we can use to most effectively accomplish that, that's what we should go with. If we can accomplish that with sensors and communication, that should be our goal. However, there are times when the only practical solution is to share a little bit more than maybe the agent would be able to get on its own.